Let's make sure that the transcript is working. Yep, looks like that's working. All right, so notice if we change directory into the directory that has the course and we list the material, we find that the lecture 6 is not here yet, so we'd better fetch the release, git fetch release, and then we'd better merge the main branch of the release into the current branch. We'll add a comment and we'll allow unrelated histories. And now if we list, we find that lecture 6 is here. So we can change directory to lecture 6. And let's start Jupyter Notebook. All right, here's the Jupyter Notebook for this week's lecture. We're done with the first third of the course. We're done with the part of the course that deals with Introduction to Python and Introduction to NumPy. And now we're starting the middle third of the course. The middle third of the course is really about sound. It's about how sound is stored on a computer and how it's understood and how it's created. Today we're starting out with the simplest kind of sound, and that is a pure tone. So let's go ahead and look up A440, for example. A440 on Wikipedia shows that this is the pure tone on the computer, or the Stuttgart pitch. It's the standard pitch corresponding to the A at the center of the piano, the fourth A on the piano. So I think I'm sharing sound. Are you able to hear that? If you're not able to hear that, then please let me know, but I think you were able to hear the A440, the center note on the piano. This number 440, what it means is that there are 440 cycles per second. Music is created by a vibrating string or a, yes, thank you. Music is created by a vibrating string or by a vibrating reed, and that vibrating reed or vibrating string causes vibrations in the air. And in this case, those vibrations have 440 complete cycles per second. It's the A above middle, that 440 hertz is the standard for the A above middle C on the computer. And it looks like a cosine. Last time, you remember we looked at cosines. Let me go ahead and find what we did last time. Let's see, let me create a new terminal here. And let me just open up the Jupyter Notebook from last time so I can show you what a cosine looks like. Here's the Jupyter Notebook from last class. And you remember that we had these cosines and sines. Here's the blue one is a cosine, the green one is a sine. Here's here's one half of a period of a cosine and one half of a period of a sine wave. I wonder if we have enough information here to let's make it go for one complete period up to 2 times pi. Let's see if that will work. Let's see if I have everything I need to do that. No, probably not. I probably need to import NumPy and Matplotlib. So let's import Matplotlib as pyplot. Oh, it's having trouble running this code. Okay, this one is not, for some reason, I'm not able to run this particular window, but you can see that the cosine starts out at 1 and goes to -1 and then back to 1. The sine starts at 0 and then goes up to 1 and then down to 0, then down to -1 and then up to +1. Right. Let me go ahead and get rid of last time's stuff. All right, let's go back to what we were working on this time. So sound is stored on a computer by storing those air pressures. Right? The pressure in the air is changing 440 times per second. 440 times per second means that it goes 2 pi radians, that's the angle, 440 times every second. So we write that x of t is the cosine of 2 pi times 440 times t, where x of t is the position of the string, or it's the air pressure of the air, or it's the position of the reed in a clarinet. T is the time measured in seconds. 2 pi is the number of radians in one cycle. A radian is a measure of an angle, and a circle has 2 pi radians. That's because the circumference of the circle is 2 times pi times the radius of the circle. And 440 is the frequency of this cosine. It's the number of cycles per second, or the number of hertz. Now, that's how the sound exists in the air. If you want to store it on a computer, you have to store a series of integers. You have to store it at a series of sampled values. And so, for example, if we sample it once every 8,000th of a second, 8,000 times per second, right? If we sample it 8,000 samples per second, then t is replaced by n over 8,000. Right? So n is the sample number, and 8,000 is the number of samples per second. So for example, let's import numpy as pi, and we'll create an 8,000 long array of zeros, and then we'll take the nth sample of that array, and we'll replace it with the cosine of 2 times pi times 440 times n over 8,000. And then let's play that. We'll play that using the IPython display toolkit, which allows us to play an audio signal. So there's that 1 second long middle A note on the piano. That's the fourth A note on the piano. And it's at exactly 440 hertz, or 440 cycles per second. In Python, in NumPy, we can do that by just taking this entire array, the range of values. You remember np.arange generates a range of values between 0 and 7,999. And if we just take that entire range of values and feed it into the NumPy cosine function, it will generate the same sequence of sample values. Let's plot that actually. Let me oh okay, this is going to show us not much. Let's try it and find out. I think I've got the same thing later on the plot, but you can see that it's kind of going up and down a little, but you can't see very much of it. And the reason is because in 8,000 samples is 1 second. In that 1 second, it's made 440 complete cycles. So let's see, if this is 440 cycles, then half of it is 220 cycles. A quarter is 110 cycles. Maybe we should cut it down to just about 1/10 of that, or maybe even just 1/20th of that. Let's choose the first 400 samples and see if that gives us something that looks. Now we can see a cosine. So you can see just in the first 1/16th of that 8,000 samples, sorry, the first 1/20th of those 8,000 samples, we can see this many sample values going up and down. So here's what it looks like. It looks like a cosine, and here's what it sounds like. All right, let's talk about that pure tone a little bit, right? Every tone has uh, 3 different parameters that govern it. Those 3 parameters are the frequency, the amplitude, and the phase. This x of t has an amplitude of 1. It has a phase of 0. The only thing that's interesting about it is the frequency. What's interesting about frequency is that there are at least two different ways in which you can represent it. F is the frequency in hertz, which is cycles per second, and F, you know, is 440 hertz. This one is at 440 hertz. But omega is the frequency in radians per sample, right? So it goes F divided by the sampling frequency, Fs samples per second, multiplied by 2 pi, which is the number of radians in a circle. And we can calculate that by taking the frequency of the cosine in hertz, divided by the sampling frequency, the number of samples per second, and then multiply that by 2 pi. And that gives us omega, which is the frequency in radians per sample. And then if I take omega and multiply that by n, I get the same result as before. Right? So this line, x equals cosine of omega times n, this is actually exactly the same line as this, y equals cosine of 2 pi times 440 times n over 8,000. In fact, if I print out x minus y is, and then let's take the sum of x minus y, the sum should be basically 0. Let me take the average. The average is 7.5 times 10 to the negative 17th, which is a very, very small value. Let me put that before the IPython display so that we still get our display. So the average value is 0, right? X minus y, this x is the same as the y that we calculated before, and it sounds the same. Okay? If you're interested in music, you might already know that every time you go up by 1 octave on the piano, let's look at a piano. So here's a piano, right? Every time you go up by 1 octave on a piano, let's see, do we have, this is just a song being played on a piano. Do we have a close-up of a piano key? No, we don't have a close-up of the piano keys. But if you go from, you see that there are these repeated patterns of black and white keys on the piano, where it has 2 black keys and then 3 black keys, and then another 2 black keys and then another 3 black keys. If you go up one complete cycle, eight notes on the piano is called 1 octave. 1 octave is actually doubling the frequency. So if we take the frequency, we go 110, 220, 440, 880, 1760, right? We can take this sequence of frequencies and play them. We'll discover that those go up by 1 octave at a time. It'll go from the A note here to the A note here to the A note here to the A note here, and then to the A note here. It will play 5 different A notes because 440 is the middle one. That's the center of the piano. 880 and 1760 are each 1 octave up. 110 and 220 are each 1 octave down. So let's play those 5 notes. You can hear that it's going up 1 octave at a time. A, A, or something like that. My singing voice is not very good. Each of those is the same note. They're all A, but each of those is 1 octave separated from the other notes. So for each of those, I'm going from this A note to this A note to this A note to this A note, just jumping by 1 octave each time. Now, if you count the white notes and the black notes, you find that there are 12 between from one A note to the next. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 steps in 1 octave, from this octave to this octave. And if doubling it means that we go up 1 octave, then in order to go up by 1 note, we have to go up 1/12 of an octave. That is, we have to go up by some multiplier g, such that g raised to the 12th power is 2, right? So the number g is the 12th root of 2. You could write that as g is equal to 2 raised to the 1/12th power. And that's exactly how I'm going to calculate it. I'm going to calculate g is 2 raised to the 1/12th power using NumPy power. Let's look up NumPy power. So NumPy power is a function that takes x1 and raises it to the x2 power. Either x1 or x2 can be array-like, or they can both be array-like if they have the same length. And then it will generate an output, which is x1 raised to the x2 power. In this case, I'm going to take 2 and raise it to the 1/12th power. And then I'm going to start at 440 hertz, and I'm going to take 440 times g to the 0 12ths, 1/12, 2/12, 3/12, and so on. Let me just do this from 0 to 12, so that should go exactly 1 octave. And so I'll take 440 times g to the 1/12th, 440 times g to the 2/12ths, etc. So you can hear that we've gone up exactly 1 octave. What we've done on the piano is we've gone from this A note, we've gone to A sharp, and then to B, and then to, oh, sorry, here's A, and then A sharp, and then B, and then C sharp, then D sharp, then E, then F sharp, then G, and then G sharp, and then finally back to A again. So we've gone through one complete octave on the piano. If you don't like using NumPy power here, you can do it the same way by just starting out with f is equal to 440. And then every time we go through this, we'll multiply f by g one more time. So when I finished, I multiply f is equal to g times f. And each time what that will do is it will multiply the previous frequency times 2 to the 1/12th power. So you see that if 1 octave is a factor of 2, then one note is 2 to the 1/12th power. One half note on the piano, one demitone. So these are the sort of the core concepts in music, I guess. We want to talk about how sound is stored on a computer. We store it by storing the samples. How sound and frequency. Oh, let me show you also. Let me do a stem plot here, just to show you that the first 400 notes are actually stored as individual samples. You can see that these are the samples that are actually being stored. Let's just plot the first 100 of them. So here's what's actually being stored on the computer. Let me print it out actually. Let's just print out the first 12 samples of Y. You can see that the first 12 samples are 1, and then 0.94, 0.77, 0.5, 0.18, minus 0.16, minus 0.48. If you look at the plot here, we can see 1, 0.94, 0.77, 0.51, 0.18, minus 0.16, and so on. So this is what's actually being stored in the computer when we hear an A440. It's just these samples that are being played back, 8,000 samples per second are being played back from the loudspeaker. All right, so what have we got? We've got how sound is stored in a computer. Now we've learned about frequency. Now let's learn something complicated that can happen when sounds are stored in a computer. You might ask, if sound is being stored as a series of numbers, how does it smoothly interpolate between those numbers? Well, the answer is exactly that. It just assumes that this curve is smooth. And if this curve becomes non-smooth, then the computer starts to have a problem. It starts to have a problem called aliasing. So here again, I'm going to plot that 440 hertz tone. Here you can see that 440 cycles is just too much to plot. And so instead, I'm just going to plot um, the first one complete period, 800 over 8,000 samples over 440 hertz. That's a little bit less than 20 samples. So I'll plot the first 20 samples of that. So here are the first 20 samples, which makes one period. Looks like it's 19 samples from sample number 0 up through sample number 18. Actually, let me plot that versus n. Uh, n is fs over 440, little n is np dot a range. Let me plot. I wonder if this will give me an x-axis. Oh, it does, but it doesn't label it correctly. Okay, excuse me. So yeah, you can see the 0th sample, the first sample, the second sample, the third sample, and so on. Here are the first 19 samples of that 440 hertz tone. And now what I want to do is I want to take this 440 hertz tone, this tone that takes 19 samples, and I want to double it in frequency and then double it again in frequency. So let me plot an 880 hertz tone, and then let me plot a 1760 hertz tone, and then a 3520 hertz tone. And what we see is that as it gets faster in frequency, here's the 880 hertz, here's 1760. So on the piano, right, we've started here with this A note. Now we go up to this A note, and then this A note, and then finally the A note at the top of the piano. And if we see those, eventually we get to an A note where it's not really obvious that this is a pure tone. Let's find out if we can even hear it. I'm not sure if we can, will we be able to hear those? Oh, let me go back here where I played them all and um, add the next higher one. So we had 110, 220, 1760. What's 2 times 1760? Let me just write 2 times 1760. 3520, I think. And let's see if we can hear that. And then let's actually try 4 times 1760. We'll find out if we can hear that. So that was interesting. 1760 we heard, the 3500 hertz tone we heard, but then the one above that seemed to go down in frequency. That's kind of odd. Why did that happen? Let's try and go one more step and see what happens. It doesn't seem like it's continuing to go up. It seems like these last two tones are doing something very strange. They're maybe going up or maybe going down. Let's find out why. What's going on is that that 3500 hertz tone, we can still hear it, and you can still kind of see that there's a cosine here, but not quite, right? You can kind of see that it's up and then down, and then up and then down, and then up and then down. But if we continue making it faster and faster, we lose that. Let me make it this easier. Let me just create a cosine that has 1, 2, 3, 4, 5 samples. And let me start out with 0 periods of a cosine that has 0 periods and 5 samples, then a cosine that has 1 period, then a cosine that has 2 periods, then a cosine that has 3 periods, and then a cosine that has 4 periods. And if I plot those, you can see that when it has 0 periods, it's just a constant, right? 0 periods. When it has 1 periods, it goes down, and then it goes up again. When it has 2 periods, you can see quite clearly it goes down and up, then down and up. But when it has 3 periods, oh look, at 3 periods, it looks exactly the same as if it had 1 period. Um, and at 4 periods, it looks exactly the same as if it had 0 periods. can show, I just add that to the description here. Uh, so 0 periods looks exactly the same as 4 periods. 1 period looks exactly the same as 3 periods. 2 periods is just fine. 3 periods looks exactly the same as 1, and 4 looks exactly the same as 0. I think you can see the problem. The problem is that when I have only 5 samples, I don't have enough samples to plot 4 complete periods. 5 samples is really only enough samples to plot as many as 2 complete periods and not more than 2, right? The problem is that the cosine of 0 is 1. The cosine of 2 pi n over 4 is a regular cosine. The cosine of 6 pi n over 4 is actually the same thing as the cosine of 2 pi n over 4, right? 1 complete period in 4 samples is the same thing as 3 complete periods in 4 samples because all we have are these dots. We don't have the values that come in between. We could plot the values that come in between. We can create something that has 400 samples in the same period. And if we plot that, then we can really see the differences, right? Here's 0 periods, 1, 2, 3, and 4. If we have these smooth curves, you can easily see 3 complete periods. But if you only have the dots, you don't get those 3 periods again anymore. And so this is what happens in your computer if you try to include too many cycles for the number of samples that you have, right? The number of samples is only enough to represent 2 periods, and if you try to represent 3 periods, it winds up being aliased. Alias means that it has exactly the same sample values, and so the aliasing means that saying that it has 3 cycles, it's exactly the same signal as if it had 1 cycle. It has the same name. And so we can plot these. Let's take 8,000 samples per second. With 8,000 samples per second, we can create a cosine of up to 4,000 hertz. When we create these higher frequencies, 5, 6, and 7,000, instead of continuing to go up in frequency, it will go down in frequency. So you see, we thought we were creating 1, 2, 3, 4, 5, 6, 7. Instead, we created 1, 2, 3, 4, 3, 2, 1. Let me change this and show you that it's exactly the same. If I call it 1, 2, 3, 4, 3, 2, 1, it will sound the same. Right? It doesn't matter whether I call it 5,000 or 3,000, it's the same. And it doesn't matter if I call it 7,000 or 1,000, it's the same. So you see, we have this phenomenon that's called aliasing. 7,000 hertz is just an alias for 1,000. Let's look up what alias means. Alias may refer to a TV series or a pseudonym. Oh, we don't have any good. Oh, here's George Sand, which was the author name for a woman named Amantine Dupin. So alias is a fake name. Her real name was Amantine, and yet she published under the name George. Similarly, William published under the name Olivier O. Henry. Right? People come up with fake names for themselves. In exactly the same way, 7,000 is actually a fake name for 1,000 hertz. And the reasons that it's fake is that you can only create a signal that's up to 1/2 of the sampling frequency. If we sample 8,000 samples per second, we can only create frequencies up to 4,000 cycles per second. If we want to really generate a 7,000 hertz tone, we have to sample at 16,000 samples per second. If I have 16,000 samples per second, then I can create sine waves up to 7,000 hertz. Let's try it. That's really higher in frequency than you can easily hear, but I think you can at least hear that it keeps going up and up and up in frequency. All right, so now we know about the problem that can arise when you try to store things in a computer. Right? When we're trying to store sounds in a computer, what we're actually storing is a sequence of samples like this. And if we try to store too many cycles, then we start to get, then it starts to break down and we get aliasing, where instead of actually being 3 cycles, it actually turns into 1 cycle. Instead of being 7,000 hertz, it turns into 1,000 hertz. Now, finally, the last bit of the lecture, I want to talk about what happens when you use a sine wave. And the reason that I'm using cosines is that if you use a sine wave, it sounds exactly the same to a human, right? And the reason is that a cosine is just a sine wave shifted in time. So if I generate a series of cosines and sine waves, I'm just going to take the cosine and I'm going to shift it by theta, where theta will be in the range minus pi over 4, minus 2 pi over 4, minus 3 pi over 4. So here's the cosine. Here's the cosine shifted to the right by pi over 4 radians. Here it's shifted to the right by 2 pi over 4 radians, and you see it's exactly a sine wave. Here it's shifted to the right by 3 pi over 4 radians, and here it's shifted to the right by 4 pi over 4 radians, and you see that it's exactly a negative cosine, right? This last plot is just exactly the negative of this first plot. So if you shift it to the right or to the left, shifting it to the right or the left, you can wind up with the negative of what you started with, or you can wind up changing a cosine into a sine. And humans can't even hear the difference. Let me play a cosine, and then let me change it. Let me shift it in to. Let me play these 5 tones. Let me play you a cosine, and then a shifted cosine, and then a sine wave, and then a shifted sine wave, and then a negative cosine. And what you'll discover is that you can't hear the difference. So the reason that we use cosines is just because it doesn't matter. You can use a cosine, you can use a sine, it doesn't matter. They sound exactly the same. In fact, let me change this to a sine wave, and then we'll discover that it's exactly the same. So you see the reason that we use cosines is because it doesn't matter. You could use a cosine, you could use a sine, it doesn't matter. It's the same. All right, for the homework, we have, I think, 3 problems this time. Let's open up the homework and take a look. So these 3 problems are minimum Fs, omega, and pure tone. Minimum Fs, we want to find the lowest sampling frequency that would avoid aliasing for a pure tone at F hertz. The input is a tone in hertz, which is cycles per second. Let's look up hertz over here. Let's see. Hertz is the unit of frequency in cycles per second. Oh, I wonder if we can play these. Let's find out. Oh no, these are images that are varying. This one is varying at 2 hertz, 2 cycles per second. This one is varying at 1 hertz, 1 cycle per second. And this one is varying at half of a hertz, which is 2.0 cycles per second. So that's a demonstration of different frequencies. Does it have tones? Oh, here's has a sine wave with a number of hertz increasing, right? So anyway, in our homework, we have minimum sampling frequency. If the tone is at a frequency of f, then we need to return the smallest possible sampling frequency that was not caused aliasing. Well, that's really easy. I just told you that that has to be at least 2 times f. And then omega, find the radial frequency that matches a given f and fs. So we're given an f and an fs, and we have to return omega. Let's go back and see if we can find that. There's G, how sound is stored in a computer frequency. Frequency, omega is equal to 2 pi radians per cycle times f over fs. Oh, I even have the formula right here. Omega is equal to 2 pi times f over fs. So let me write that here. Omega is equal to 2 times numpy dot pi times f over fs. That should solve that problem. And then the last problem on the homework is create a pure tone that's n samples long with a frequency of omega radians per sample. Well, that's just exactly what we showed here. That's the cosine of omega times n. It doesn't matter if it's a cosine or a sine, but let's use the cosine. Omega times, oh, we need a little n here. So we need to specify little n. Little n was numpy dot a range capital Fs, but now we don't want Fs samples. Now we want capital N samples. So n is equal to numpy a range with a length of capital N samples. All right, that should be everything we need. Let's go check it out. All right, homework 6, problem 1. Problem 1, oh no, it looks like it's died. I'm going to quit this and restart because it looks like my server has died. All right, let's go ahead and run everything. All right, problem 6.1, minimum fs. Here's the help on that function, telling us, remember that we need fs is greater than or equal to 2f. And so when we set it up, the fs should be 880, and we got fs is 880. Now let's try omega should be 2 pi f over fs. So we should get omega, if little f is 1,000 and fs is 8,000, then omega should be 2 pi times 1,000 over 8,000, which is pi over 4, which is about 0.785. And we get omega is 0.785. And then finally, if we um, if we generate a pure tone with a frequency of 440 hertz, we should get a stem plot that shows that tone at 440 hertz. And there it is, 19 samples for that tone, 18 samples shown here. All right, let's try running the grade.py and see if it gives us 100%. Grade.py gave us 100%. Let's just check to make sure that it looks good on the computer. On my computer, it looks good. So let me run GitHub Desktop in order to check it in. And let me push it to origin. It's taking a minute for it to push. There we go. Now we're pushed. And let's go ahead and check on GitHub to make sure that it got checked in. I think I'm probably going to have to change my username on GitHub. Let's find out. Yes, I'm logged in with my teacher account. Let me log in with my student account. Here we go. Now I'm logged in with my student account. Let me go to lecture 6 and make sure that the homework is correct. Go to lecture 6, open homework 6, make sure that it shows your changes. Fs is equal to 2 times f. Omega is 2 pi f over fs. And x is equal to the cosine of omega times n. All right, let's take this URL And let's go to Canvas and check it in as a homework. Looks like my browser takes a little while to get going. I guess login takes a while. More than a minute already. That's unusual. I wonder if it would be faster if I tried again. Oh, there we go. Much faster this time. All right, right. So go to Canvas. And on Canvas, you should be able to take this URL from your working homework and go to your Canvas page and just check it into homework 6. If you go to homework 6, you should see that it will say enter the URL for your copy of homework6.py. And in this place, you can enter the URL for your homework online that shows this completed work. All right, now that we've done that, let's go ahead and take attendance. Let me stop the recording.